In this video, I'd like to talk about covalent bond energies. Begin with the question, why do covalent bonds form? Well, pretty much the answer to anything in it is to minimize the potential energy of the system. Remember, bond formation is an exothermic process. When we go from separate atoms to bonded atoms, we are lowering the potential energy of the system, so bonds form to minimize the potential energies of the atoms involved. Let's consider a hypothetical reaction in which we take 1 mole of methane, CH4 in the gas phase, and add sufficient energy to separate it into the 5 atoms that make it up. Measuring that energy shows us that it requires 1,652 kilojoules of energy. Suppose I carry out the reverse process and ask myself how much heat would be released when I allow 1 mole of carbon atoms in the gas phase and 4 moles of hydrogen atom in the gas phase to come together to form 1 mole of methane. Well, you guessed it, the same amount, 1,652 kilojoules, negative this time because bond formation is an exothermic process. Our model is that 1 molecule of methane consists of 4 equivalent CH bonds. Remember, it's just a model. All we really know is that those 5 atoms consist of 4 hydrogen atoms in a tetrahedral orientation with a carbon atom in the center. So if I wanted to calculate the average energy of each bond, I would simply take the 1652 kilojoules required to break all 4 of them, divide it by 4, and obtain an average carbon-hydrogen bond energy of 413 kilojoules per mole. Scientists have done lots of experiments like this and tabulated the bond energies of lots and lots and lots of covalent bonds. And on the next slide, I will show you a table I created that shows average bond energies in kilojoules per mole for a whole bunch of bonds. The ones in the chart are all single bonds, but I've got down here some multiple bond energies as well. Now, these are all given as positive quantities because they refer to the amount of energy required to break 1 mole of bonds. In the old days, these used to be called bond association energies, or BDEs. They are positive quantities, again, because bond breaking is an endothermic process. They are average bond energies because there are lots and lots of different types of bonds. There's no single type of carbon-carbon bond or carbon-hydrogen bond, and the actual bond energy will vary slightly from molecule to molecule. Nonetheless, as you'll see, it is quite useful to have average bond energies. So, what can we do with these? Well, let's consider the reaction of 1 mole of hydrogen gas with 1 mole of fluorine gas to form 2 moles of hydrogen fluoride gas. In this process, we are breaking 1 hydrogen-hydrogen bond and 1 fluorine-fluorine bond, each of which is an endothermic process. And we are forming 2 hydrogen-fluorine bonds, which is an exothermic process. Can we calculate these quantities? We can if we have the corresponding HH, FF, and HF bond energies, which we do because they're on the table on the previous slide. So let's see what these quantities look like. To break 1 HH bond, I must put in 432 kilojoules of energy. That's the HH bond energy. To break 1 fluorine-fluorine bond, I need to put in 154 kilojoules of energy. To form 2 HF bonds, I get out twice the HF bond energy, so that's negative 2 times 565 kilojoules. When I add these up, I see that my estimated enthalpy change for this reaction is negative 544 kilojoules as the reaction is written. Now, we can actually compare this to a literature value because, as you may have recognized, what we're doing in this reaction is forming hydrogen fluoride gas, a compound, from its elements in their standard states. The enthalpy change for that is equal, of course, to the standard enthalpy of formation. Because I'm forming 2 moles of HF gas, the enthalpy change should be twice the standard enthalpy of formation of HF, which according to the thermodynamic tables is negative 542 kilojoules per mole. So we see our estimate using bond energies was pretty darn accurate. Let's do a couple more examples. So what we're doing here is using bond energies to estimate the enthalpy change for a reaction, and we're going to apply our old friend Hess's law. Remember, in Hess's law, we can make up any pathway we want because enthalpy is a state function or a state property. It is pathway independent. So the pathway we imagine is we take the reactant molecules and we put in sufficient energy to completely break every single covalent bond in every reactant compound to make the atoms. The energy required for that process is the sum of the bond energies of all the reactants. In our second step, then, we take those free atoms and allow them to come together and form every covalent bond in every molecule of the products. The energy change for that process is the negative of the sum of the bond energies of the products, because formation of the products from the atoms is an exothermic process, so we take the negative of the bond energy. We can write a simplified version of this as delta H is approximately equal to the sum of the bond dissociation energies of all the bonds that are being broken minus the sum of the bond energies of all of the bonds being formed. Uppercase D is a somewhat archaic symbol that represents the bond dissociation energy, probably from the word dissociation. And we'll again ask the question, why is this just an estimate? And that's because, again, the tabulated bond energies are averages and may be somewhat different than the actual bond energies in the molecules in your reactants and products. So now let's do some examples. Let's use the bond energies to estimate the enthalpy change for the formation of 2 moles of ammonia from 1 mole of nitrogen and 3 moles of hydrogen. In these problems, you need to know not only how many bonds are present in your reactants and products, but what types of bonds they are. So it's really important to first draw out the Lewis structures so you know what kinds of bonds you're dealing with. So in this reaction, we've got a nitrogen-nitrogen triple bond, a hydrogen-hydrogen single bond, and 3 nitrogen-hydrogen single bonds. My equation is the enthalpy change is approximately equal to the sum of the nitrogen-nitrogen triple bond energy plus 3 times the hydrogen-hydrogen single bond energy, because I'm breaking 3 hydrogen-hydrogen bonds, minus 6 times the energy of the NH bond, because in this process, in forming 2 moles of ammonia, I'm forming 6 moles of NH bonds. I look at my corresponding values on the table, and I obtain a value of negative 109 kilojoules per mole of reaction as it's written. I'm simply writing kilojoules for simplicity here, but it implies for this reaction as it is written here. Now you may notice that if this is occurring in the gas phase under standard conditions, this should be equal to 2 times the standard enthalpy of formation of ammonia, which is negative 92 kilojoules per mole. So as you can see, this estimate gives us a pretty decent ballpark estimate, but it's not exact. That's about 15% off, but I think that's reasonable because, again, it's a not too far off estimate. Here's another example. Use the bond energies to estimate the enthalpy of combustion of 1 mole of acetylene. I'll write and balance the equation. 1 mole of acetylene will form 2 moles of carbon dioxide and 1 mole of water. That gives me 5 oxygen atoms on the product side. So to get 5 oxygen atoms on the reactant side, I will need 5 halves O2. And it's perfectly fine to use fractional coefficients. Here are our Lewis structures. Acetylene has a carbon-carbon triple bond. Oxygen has oxygen has an oxygen-oxygen double bond. Carbon dioxide has a CO double bond, 2 CO double bonds. Water has 2 OH single bonds. I'll write out my equation. The enthalpy change is approximately equal to twice the carbon-hydrogen bond energy plus the carbon-carbon triple bond energy plus 2.5 times the oxygen-oxygen double bond energy minus 4 times the carbon-oxygen double bond energy minus 2 times the OH bond energy. I'll plug my values in, and I want to point out something really important here. If we go back to the table, for the carbon-oxygen double bond energy, we see an average energy of 745 kilojoules per mole, but it turns out that in carbon dioxide, for reasons I can explain in class, the carbon-oxygen double bond is substantially stronger. And since there really is only one type of CO double bond in CO2, it has its own unique value, and as you can see, I used that value here. Do the calculation, and I get a value of negative 1,228 kilojoules per mole of reaction as written, which is not that far off from the literature value. One final problem is using enthalpies of formation of species to estimate a bond energy. Here I give you the standard enthalpies of formation of sulfur in the gas phase, fluorine in the gas phase, and sulfur hexafluoride in the gas phase. First off, you might ask yourself, aren't sulfur and fluorine elements? Why are their standard enthalpies of formation not equal to 0? Think about that for a minute. Standard enthalpy of formation involves the formation of the substance from 1 mole from its constituent elements in their standard states. Gaseous sulfur is not the standard state of sulfur, and monatomic fluorine is not the standard state of fluorine. So what are we going to do here? Well, we're given sulfur hexafluoride, sulfur, and fluorine. If you think back to the first slide, we saw that if we knew how much energy it takes to separate 1 mole of methane into the atoms that make it up and divide that by 4, that gives us an average carbon-hydrogen bond energy. So maybe I can use this information to calculate the enthalpy change associated with breaking up 1 mole of sulfur hexafluoride into its constituent atoms and use that quantity to estimate the SF bond energy. Well, if I can calculate the standard enthalpy change for this reaction, which I can, given the standard enthalpies of formation of reactants and products, that quantity should be 6 times the sulfur-fluorine bond energy, because in carrying out this process, I am breaking 6 sulfur-fluorine bonds. So we'll use our Hess's law equation from way back in chapter 6. The standard enthalpy change for reaction is equal to the sum of the standard enthalpies of formation of the products minus the sum of the standard enthalpies of formation of the reactants. I'll plug in the values I'm given above, and I see that for the first equation written, the enthalpy change is plus 1962 kilojoules per mole. Makes sense that it's a positive quantity because bond breaking is an endothermic process. I'll divide that by 6 to give me an average bond energy of 327 kilojoules per mole in sulfur hexafluoride. I looked it up on the internet and I found a value of 343 kilojoules per mole. And again, that's because there are lots of different types of sulfur-fluorine bonds. All we can say for sure is that in sulfur hexafluoride, that has a value of 327 kilojoules per mole. That's about it for bond energies. Next, we'll talk about molecular geometry.